This lecture is going to be on eigenvectors, which you can think of as some special vectors that are associated to a linear transformation. Now, eigenvectors are really the key to many of linear algebra's applications. But the good news is it's not a difficult concept, so conceptually it's pretty easy to understand. However, actually computing eigenvectors is going to use basically all of the concepts we've covered so far in this course. Okay, so we're going to see linear transformations, thinking about linear transformations geometrically. We're going to compute some null spaces of matrices, bases for the null spaces. We're going to see determinants. We're going to use the properties of determinants. So basically everything we've covered. Okay, so I'd like to start with an example just to show you, in very plain terms, what an eigenvector looks like. So let's start with a linear transformation from, well, I'll just give you the matrix. So what linear transformation does this represent? This matrix here. Well, it represents the transformation from R2 to R2, where T of x is given by multiplication by this matrix A. Okay. Well, there's nothing really special about this transformation, but let's consider what happens when we input various vectors. So for example, what happens to the vector 1, 0? Well, it gets sent to 6, 5. Right? The first column, in fact, is exactly has a meaning of where 1, 0 gets sent. How about, well, let's just pick a random vector 1, 3. Well, this gets sent to 0, 2. Right? Because we're taking 1 of this column and 3 of this column. So we have 6 minus 6 is 0, and we have 5 minus 3 is 2. Okay. Yeah, nothing really special going on here, right? So, for example, we have 1, 0 that's getting sent to, 6, 5. What's it going to look like? It's going to go way up here. So this is what T does to 1, 0. Let's do another color for 1, 3. So 1, 3, that's this vector here. That's going to get sent to 0, 2. Okay, I mean, it looks kind of random, right? Okay, now I'm going to give you a special vector, 1, 1. Wow, what's so special about that? Well, nothing really, but there's something special about this vector connected to this linear transformation. Where does it get sent? Again, I have 1 in the first column plus 1 in the second column, so I get to 4, 4. Now this is interesting, because let me again draw my transformation. What's happening to 1, 1? After I apply my transformation, you see what's happening is it's pointing in the same direction that it was before, but it's larger now. Okay, this is in the exact same direction it was before. And I can give you one other special vector. What is it? It's 2, 5. Where does this go? Well, if you do the computation, just multiply by that matrix. It turns out this gets sent to itself. Okay, so 2, 5. That's this vector here. That just gets sent to itself. Okay. Whereas this vector 1, 3, it just kind of got sent somewhere random. Right? And same with 1, 0. Okay. However, these two vectors, these are called eigenvectors. So these are eigenvectors. of the matrix A, we would say. And you can see the linear transformation sends them to another vector that's in the same span. Right? So 1, 1 got sent to just a multiple of 1, 1. And 2, 5 got sent to, in fact, itself. Right? So whenever we have both of these kinds of behaviors, we call these eigenvectors. So let's define what an eigenvector is. So let's let A be a matrix, but not any kind of matrix. We're only going to be talking about square matrices. So let A be an n by n matrix, square matrix. Then let's say non-zero vector. Just by definition, we don't want eigenvectors to be the zero vector, so that's not very interesting. So a non-zero vector in Rn is called an eigenvector. It's called an eigenvector of the matrix A if, what should our definition of eigenvector be? Well, if when we multiply by the matrix A, we just get a scaled version of the original vector. Okay, so it has to be v times some scalar. Okay, for some scalar. And lambda, this letter here, this Greek letter, is typically used for the scalar. Okay, so that's just a number, a real number. Okay, and then here, also this lambda has a name. It's not an eigenvector. It's not a vector, right? It's a scalar. But it's called an eigenvalue. And we say v. Okay, so this v is the eigenvector associated to lambda. So v is the eigenvector associated to the eigenvalue lambda. Okay. So in the previous example, we had an eigenvector 1, 1. That corresponded to the eigenvalue. What is the eigenvalue associated to this eigenvector? Well, when we did A times V, we got 4 times V, right? And multiplied by 4. So this lambda is 4. And how about my other eigenvector? 2, 5. Oh, by the way, I should say, they're not just 2 eigenvectors here. Because, you see, 2, 2 would also be an eigenvector. That would go to 8, 8, just by what we know about linear transformations, right? If you scale anything in the domain and then apply the transformation, that will just be a scaled version of the image. Okay, so anything pointing in the direction of 1, 1 will get sent to, 4 times that vector, essentially. And the same for this vector. But yeah, let's say we take 2, 5. What is the eigenvalue corresponding to 2, 5? Well, it's 1, right? Because A times 2, 5 is just 2, 5. It's just 1 times V. Right? All right, let's do a bunch of examples. So let's make it interesting. Let's do a 3 by 3. But we'll keep the matrix relatively simple so we can interpret it as a linear transformation. How about this one? So it's the identity matrix, but I put a -1 in there. Can you see what this matrix is doing? What is a linear transformation? Let's draw a 3-dimensional space. So let's say this is 1, 0, 0. This is my 0, 1, 0, and this is my 0, 0, 1. Well, you see it's fixing 1, 0, 0 and 0, 0, 1, but you see it's sending 0, 1, 0 to 0, -1, 0. So this one is getting sort of it's getting flipped this way. So what kind of transformation is this? Well, it's a reflection, right? It's a reflection across the xz plane. So here's the plane that I'm reflecting across. Because anything in the xz plane will just get sent to itself. But then 0, 1, 0 is getting sent to 0, minus 1, 0. So this is a reflection across the xz plane. Okay, in 3 dimensions. So I'm reflecting across. What are the eigenvectors? Can we see what the eigenvectors are? What are the eigenvectors? Well, are there any vectors that get mapped to themselves? Yes, I mean there's a whole plane of eigenvectors here. Anything lying on the so any vector lying on the xz plane, well, except the 0 vector. Okay, except the 0 vector. This is because we don't consider the 0 vector an eigenvector. But any other vector lying on the xz plane, it just gets mapped to itself. So we would say it's an eigenvector with eigenvalue 1, right? Because A times V is just V, right? If we're lying on the xz plane, if we have no y coordinate, then this matrix A just acts like the identity. Are those all the eigenvectors, though? Well, no. There's another one. Do you see what the other one is? Look what happens to, right? So what if I do A times 0, 1, 0? That gets sent to 0, minus 1, 0. But you see that is minus 1 times 0, 1, 0. Okay, so AV equals minus 1 times V. I just found an eigenvector with eigenvalue minus 1. Okay, so this is an eigenvector. So we have a whole plane of eigenvectors that we already found, but here's another eigenvector. And basically the whole line spanned by this also will work. This is an eigenvector with eigenvalue lambda equals minus 1. Okay, it gets reflected in the opposite direction. Or are there any others? Like, what if we had a vector pointing out this way? Okay, well that would get reflected here. See, but see, it would not be pointing in the same direction. And it wouldn't even be pointing in the opposite direction. So we can't even say it's a negative scalar times itself. So it turns out there aren't any other eigenvectors. The only eigenvectors here are actually this blue plane here, and actually anything also lying on the y-axis. Okay, the ones lying here have eigenvalue minus 1, and the ones lying on this plane, they just get sent to themselves, so they have eigenvalue 1. Okay, how about, well, here's an interesting one. How about this matrix? 0, 1, minus 1, 0. What does this linear transformation do? We've seen this one before. It sends 1, 0 to 0, 1. And it sends 0, 1 to minus 1, 0. That's over here. So this is the reflection, right? This is or not a reflection, sorry. What's the word? Rotation. Yes, so this is a 90-degree counterclockwise rotation. Well, what are the eigenvectors of this matrix? What vectors end up pointing in the same direction after I apply the transformation? This one is fun to think about, right? So, well, if I apply a 90-degree transformation, everything is pointing 9 degrees from where it was before. So there are actually no eigenvectors. And that's because no vector ends up pointing the same direction. Or even the opposite direction, right? We're allowed to have vectors that end up pointing the opposite direction. That's a scalar of -1. But we don't have that when we're dealing with a 90-degree rotation. Okay, so there are no eigenvectors for the 90-degree rotation matrix. It turns out the story is a little bit more complicated than that, but we'll get to that in due time. Okay, I think it's now time to talk about, so I kept these examples simple so we could interpret them geometrically. But what about this matrix? How did I come up with these two vectors, 1, 1, and 2, 5? So let's talk now. So in general, how do we find eigenvectors? It's a general method that we'll always find them. Okay. And we're just going to use a definition. So let's start with the definition of an eigenvector. An eigenvector is something that satisfies this equation. A times the vector is just scaled by some lambda. Okay. And here's what I'm going to do. I'm going to move both of these terms to one side of the equation. So what do I end up with on this side? Is it the zero vector, the zero matrix, the zero scalar? What do I put here? Well, these are both vectors, right? A times a vector is a vector. Lambda times a vector is a vector. So I get the zero vector here. And you see, I would love to factor out this v here, but you see the problem is I would get this. A minus lambda. I mean, lambda is a scalar and A is a matrix, so this doesn't mean anything. This doesn't mean anything. Okay. You can't subtract a scalar from a matrix, right? I mean, you can't even subtract a matrix from a matrix often. They have to have exactly the same dimensions. So how do I deal with this? Well, I'm gonna use a trick here. This is a great trick to remember. I'm going to turn this lambda into a matrix by rewriting V as V times the identity matrix. All right, so the identity matrix times any vector is just the vector itself. So V is the same as IV. And let's keep my lambda here. But now I'm going to sort of rewrite the parentheses here. I'm going to now factor out the V. Let me just write this whole equation again. So I have A minus lambda I times V. Okay, I'm doing the distributive property of it in reverse, factoring out the V. Now this is a matrix, right? What is this matrix lambda I? Well, it's just lambda. It's a scalar lambda times the identity. So identity has ones down the diagonal. So this one will have lambdas down the diagonal, zeros everywhere else. All right, so that's what lambda I is. And so I do A minus this matrix, which is lambdas, down the diagonal. And I get a new matrix. So I basically subtract off lambda from all the elements of it, the diagonal elements of A. I get this new matrix. Well, let's just look at this equation, right? I have some matrix times a vector is 0. Okay, that V is going to be the eigenvector. So when will V be an eigenvector? It will be an eigenvector. Yeah, let's write this down. So V is an eigenvector of my original matrix A if, what can we say? If this matrix times V is 0. In other words, if V is in the null space. Capital N, right? The null space of this new matrix, A minus lambda I. Interesting. So we need to look at the null space of this A times lambda I. And again, I don't even know what lambda is. Right? I'm just saying there's some lambda that I don't even know, right? So I'm trying to find eigenvectors, but I just say, there's some lambda that's scaled by. I need to look at the null space of this matrix. But you see, for most lambda, the null space is only going to contain the 0 vector. Right? It could have a 0-dimensional null space. And we want v to be a non-zero vector. Okay, so we want to choose lambda so that the nullity, the dimension of this null space of this matrix, is not 0, right? Or else we will not be able to find any vectors in it other than the 0 vector. So first of all, we want there to be some vectors in this null space, right? And so when is the nullity going to be greater than 0? Well, we have our unifying theorem, right? So if the nullity is 0, that means that our matrix is invertible. If the nullity is not 0, our matrix is not invertible. So we want this to not be invertible. And the easiest characterization of a matrix not being invertible, let me grab the unifying theorem here. Yeah, it's this one here. So a matrix is invertible when its determinant is non-zero. A matrix is not invertible when its determinant is 0. So I'm just going to go ahead and write down, I want the determinant of this matrix here to be 0. Okay? Because this is in other words, yeah, A minus lambda I is not invertible. There's something in a null space other than 0, which is equivalent to the determinant being 0. Okay. Why did I jump to the determinant, right, when I could have chosen one of these other things? Well, because the determinant is just it's easy to calculate, right? So if we have this matrix, we can just write down what the determinant is. And in fact, it's going to be some polynomial. So let me write that next. Before I get too carried away here, I'm going to jump into an example too. But yeah, but yeah, this is the key. Okay, in order to have any chance of finding an eigenvector, we need a determinant of this matrix to be 0. Okay. So note this all important. Yeah, let's actually box this. Not a determinant of the original matrix, that might not be 0, but a determinant of this matrix A minus lambda I. So this thing here, determinant of A minus lambda I, is going to be a polynomial. That's really nice. In what's my variable? My variable is lambda, right? Like I said, we haven't determined what lambda is yet. So that will give us a strategy. We have a polynomial. We set it equal to 0. Okay. So we first find the eigenvalues. Even though we set out to find eigenvectors, we end up first finding the eigenvalues and then the eigenvectors. How do we find the eigenvectors? Well, once we find the eigenvalues, we know what null space we're looking at. Right? We've pinned down lambda, and then we just look at the null space and we find the eigenvectors. Okay, but this is all pretty abstract. Let's do an example. Let's do the example that we did at the beginning, actually. And I'll show you how I found those two vectors, those two special vectors. 6, 5, minus 2, minus 1. Okay. I want to find the eigenvalues of this matrix. And along the way I'm going to find, the eigenvectors. And along the way I'm going to find the eigenvalues. What do I look at? I look at this, the determinant of A minus lambda I. And again, lambda I'm just kind of thinking about as an unknown at this point. But yeah, what is this A minus lambda I? It's this matrix minus lambda times the identity. That's this matrix. Lambda, 0, 0, lambda, right? So I get this funny looking matrix. 6 minus lambda, and minus 2 minus 0, that's just a minus 2. 5 minus 0, and then minus 1 minus lambda. Okay. That's A minus lambda I. Now I look at the determinant of this matrix, which again you can denote by these straight bars. So this means determinant. What is the determinant of this matrix? Well, it's a 2 by 2 matrix, so it's just AD minus BC. So the determinant will be 6 minus lambda times minus 1 minus lambda minus 2 times 5, which is, okay, I need to expand this out. So I get minus 6, and I have 1 lambda minus 6 lambda, which is a minus 5 lambda. And I get a lambda squared, minus lambda times minus lambda. And then I have a plus 10. So what I get is a lambda squared minus 5 lambda plus 4. That's what I meant when I said, yeah, this is a polynomial in lambda. So we get a quadratic polynomial in this case, and it turns out the degree of that polynomial is always going to be the dimension of the matrix. So 2 by 2 matrix, we get a quadratic polynomial. What do we want to do? We want to set this equal to 0, right? We want to set the determinant equal to 0 and then solve for lambda. So we're now going to set this equal to 0 and solve. How do I solve this? Well, I can try to factor. I need two numbers that multiply to 4 and add to minus 5. I know two numbers like that, minus 4 and minus 1. Which tells me lambda equals 1 and lambda equals 4. Okay. Cool. So these are my eigenvalues. See, I find the eigenvalues first, and now to find the eigenvectors. So now to find the eigenvectors. How do I do that? Well, this can sometimes take a while, but let's take our first eigenvalue, lambda equals 1. Well, then I look at I'm looking at this null space. I'm looking at a null space of A minus lambda I. So I'm looking at A minus I. What matrix is that? You see, it's this matrix, but I need to subtract 1s along the diagonals. So 5, 5, minus 2. See, this 5 and minus 2 don't get affected. Then that minus 1 becomes a minus 2. Okay, this matrix looks like it is not invertible, right? Is that supposed to happen? Yes, right? Because that's exactly what we wanted. Right? We wanted the determinant of this matrix to be 0. So we found one of the lambdas that make that work. If you subtract a 1 off the diagonal, you get something that's not invertible. And then we want the null space of this matrix. Okay? And we can do that in a standard way, but there's often a faster way to see what a null space is. So what is the null space? The null space is, right, I mean, this is a null space, right? I want to find a vector multiplied by this matrix to get 0. In other words, I want to find scalars so that I can find a linear combination of the two columns equaling the 0 vector. But you can kind of see what those scalars are, right? Because if I multiply this first one by 2 and I multiply the second one by 5, I have 10, 10, and then minus 10, minus 10. And I can just add them and get 0. So here's my vector that's in a null space. I take 2 of the first column, and then I take 5 of the second column. So this is in a null space. You can also find that by solving the system of equations, but it's often easier to just see what combination of the two columns gives you the 0 vector. Often you can just kind of eyeball it. Yeah, so what is a whole null space? Well, a null space is actually just the span of this vector. Okay. How do I know there's not a second vector? Well, it's because this matrix has rank 1. Right, and so the rank plus the nullity is 2. Again, we're using everything from this class. The rank plus the nullity is 2, so the null space is one-dimensional only. Okay. Yeah, so this is my first eigenvector. Okay, I've actually found a whole span of eigenvectors associated with lambda equals 1. How about lambda equals 4? What do I look at now? I need to look at a null space of a minus 4i. So what is a minus 4i? I take 4 off the diagonal. So 6 minus 4 is 2. Minus 1 minus 4 is minus 5. So this one. And can you really quickly tell me a vector in a null space? Or in fact, yeah, what is the whole null space? A minus 4i, sorry. What is the null space? It's the span of... What combination of the columns gives me the 0 vector? 1, 1, right? I just added 2 columns and I get 0. So there's my second eigenvector. Let's make sure we did this right. Are these the 2 that we got at the beginning? Yes. 1, 1, and 2, 5. And this is how I figured them out. So I did this calculation here. Okay, very cool. So yeah, again, this is an eigenvector with eigenvalue 4. And this is an eigenvector 2, 5 with eigenvalue 1. So 2 special vectors associated with this matrix A. Okay. Well, let's do 1 or 2 more examples. Oh, by the way, yeah, what if A is the rotation matrix that we saw before? What do we look at? We look at A minus lambda I. Or we look at a determinant of A minus lambda I, and we want that to be 0. So what is it in this case? Well, A minus lambda I, so it's a determinant of... See, lambda I is just, you're just subtracting lambda from the diagonal. So I get minus lambda, minus 1, 1, minus lambda. What's the determinant of this? It's lambda squared plus 1. And so then I set this equal to 0. But this has no solutions, right? No solutions into real numbers. Right, the solution, this would be lambda squared equals minus 1. So solutions would be I and minus I. This has no solutions into real numbers. And so that corresponds to the fact that this transformation did not end up having eigenvectors. Okay, so there aren't even any eigenvalues. Technically there are eigenvalues. They're complex eigenvalues, so that's a whole nother story. We'll get to that eventually. Let's do a 3x3 example. How about this one? 1, 0, 0. Let's keep it pretty simple. So 0, 2, 1, 0, 0, 1. Okay, and yeah, again we want to look at a determinant of A minus lambda I. We want to set that equal to 0. So what is this? It's the determinant of 1 minus lambda, 0, 0, 0. 2 minus lambda. See, you just subtract lambda off the diagonal. And this one's 1 minus lambda. And keep everything else the same. Well, what is this determinant? Well, remember the determinant of a 3x3 is tough to calculate in general. But not this 3x3. That's because this is a triangular matrix. It's almost a diagonal matrix even, except for that minus 1. But it's a triangular matrix, which is just as good because, do you remember what the determinant of a triangular matrix is? It's just the product of the diagonal entries. Because the determinant is, I have this factor twice actually, so 1 minus lambda squared times 2 minus lambda. That's the whole determinant. And I want to set that equal to 0. Okay. What are the values of lambda that satisfy this equation? Well, definitely don't expand this out, right? This is already perfect, right? It's already factored. We're not even subtracting something here. So it's already factored. So we see the values of lambda that are going to satisfy this. It's 1 and it's 2. Okay. Let's look at 1. So those are our eigenvalues. Notice we only got 2 eigenvalues, even though we had a degree 3 polynomial. That sometimes happens. Because they have to be counted with multiplicity. So yeah, we would say this one has multiplicity. Actually, I'll call it algebraic multiplicity. Two. Because it actually occurred twice as a root. This is going to have some meaning, actually, but we'll see that. So yeah, what if we take lambda equals 1? Well, let's look at, we want to find a null space of a minus 1i, right? So it's a minus I. That's 0, 1, 0 now in the diagonal. I get this matrix. Well, yeah, what's the null space of this matrix? Again, can we do this pretty quickly? Avoid those long null space calculations. Looks simple enough that maybe we can do it quickly. So again, what is a null space? Well, it's telling you what linear combinations of the column equal to 0 vector. Here's an easy one. I'll take the first column and then just not any of the second and third columns. Right? So I should say it's a span, right? The null space is going to be a span of this vector. And see, I put a comma because I knew there was another one, because this is rank 1. This is rank 1, so it's going to have nullity 2 by the rank nullity theorem. There's only going to be one. There's only one pivot there. So can I see a second way to add the columns to get 0 that's linearly independent with this one? Sure. I'll take none of the first column, 1 of the second column, and minus 1 of the third column. Okay, so that's saying that's going to be in a null space. These are linearly dependent, and I have 2 of them, so these span a null space. This is a basis for the null space. In fact, sometimes you even hear the word eigenbasis. This is an eigenbasis for this lambda. Okay, so this is one of the cases where it's kind of like this case. I have a whole 2-dimensional space spanned by eigenvectors. Okay. How about the other one? Lambda equals 2. Well, yeah, let's look at a minus 2i. That's going to be minus 1, 0, minus 1 now. And this time, this matrix looks like it's going to have rank 2. So it'll have nullity 1. The null space of a minus 2i, I don't want to write the whole matrix again, is now just going to be the span of, can you see a vector in a null space? How do I add the columns to get 0? Oh, there's an easy way. I just take 1 of the second column and ignore the first and third. Right? Cool. Okay. So what's going on here? There's something interesting going on here. This eigenvalue, lambda equals 1, it appeared twice, right, as a root of the characteristic polynomial. Did I ever introduce that word, characteristic polynomial? I should do that. So going back up here, so this is called the characteristic polynomial. It's because it's so important. This thing here, it's called a characteristic polynomial. Okay, when you take the determinant of a minus lambda I, it's a characteristic polynomial. And you set it equal to 0 and you find the roots. Okay. So you see, lambda equals 1 was a double root of my characteristic polynomial, and it corresponded to a two-dimensional subspace. Lambda equals 2 was a single root. That corresponded to a one-dimensional subspace. First thing is, so note, why are these subspaces? Well, it's because they're in a null space, right? So note, the eigenvectors associated to any single eigenvalue lambda form a subspace. That's not true, actually. Why is that not true? Because 0 is not an eigenvector, but 0 must be in any subspace. So how should I rewrite this? The eigenvectors associated to any single eigenvalue lambda plus the 0 vector plus the 0 vector. If you add in a 0 vector, then you get a subspace. Okay. And so I'm going to denote by E, all the eigenvectors associated to lambda, to be the subspace, of eigenvectors. Associated to lambda. And this is sometimes called, again, I don't want to throw too many terms at you, but this is called the eigenspace. Eigenspace associated to lambda. So again, what do we observe? We observed that, can we use this new language? So lambda equals 1 was a double root of this characteristic polynomial, and it's associated to a two-dimensional eigenspace. And the single root of the polynomial is associated to a one-dimensional eigenspace. So we might say, this turns out not to be true actually, but we might say that the algebraic multiplicity, the multiplicity of the eigenvalue in the characteristic polynomial, tells you the dimension of the space of eigenvectors. But that's not true in general. Let me just do a couple examples of that. So define the geometric multiplicity of the eigenvalue lambda to be the dimension. So again, we're kind of using this example as to try to understand this. To be the dimension of the eigenspace associated to lambda. Okay. So here for lambda equals 1, we had a two-dimensional eigenspace. So here the dimension of this E1 was 2, and here the dimension of E associated to lambda equals 2 was 1. And again, we noted that these appear to be related to these values, the exponents. You see, 1 appeared twice as a root in the characteristic polynomial. 2 appeared once as a root. But yeah, this is not in general true. But there is something that is true. I'm just going to mention. I'm not going to explain why this is true because it's really complicated. But so in general, the algebraic multiplicity is at least as much as the geometric multiplicity. But a geometric multiplicity might be much smaller. Okay, but in this example, they're equal. So can we see some examples where they're different, just to kind of give you an idea of, yeah, just how complex this situation is. I said this wasn't going to be complicated, but actually it is pretty complicated. So there are many different possibilities for, yeah, how many eigenvectors you can get. So what we're saying, if this is less than that, strictly less than that, then they're sort of missing eigenvectors somehow. So let's just look at some examples. Because again, you can't really understand these concepts until you do a bunch of examples. So how about this matrix? Can you tell me the, let's see. Actually, yeah, can you tell me the eigenvalues and the eigenvectors? Here's an eigenvector. 1, 0. Because where does that get sent? That gets sent to 3, 0. So that's an eigenvector that, see, this just gets multiplied by 3. So it's lambda equals 3. You don't need to do that whole calculation. Determinant of A minus lambda I. This is an example where you can just kind of see it. And there's another eigenvector. What is it? Well, of course, it's 0, 1. Because that just gets multiplied by 4. Right? Are there more eigenvectors, by the way? Well, sure, right? You can, like, 2, 0 is an eigenvector as well. But let's look at a picture of this. So all this transformation is doing is it's taking 1, 0, and it's stretching it out to 3, 0. So I'm stretching by a factor of 3 that way, and I'm stretching by a factor of 4 this way. You see, if I have any other vector like this, it'll kind of get stretched to the side. So 1, 1 gets sent to 3, 4. And that will happen for any other vector I have out here. So they're really just, each of these corresponds to a one-dimensional subspace of eigenvectors. So I have that axis, and I have this axis. All my eigenvectors lie on these two axes. Okay. This is the typical example. So what about weird examples? So what if I have, yeah, so here's another example. I have A equals, and by the way, this was also a fairly typical example. We had two eigenvalues, okay, and they each corresponded to eigenvectors. Okay, so we had some eigenvectors going this way along this blue line, and we had some eigenvectors going along this purple line. Okay, that's a nice situation. Here's a different situation. So we have a two-dimensional, again, transformation from R2 to R2. What are the eigenvalues, let's say? Well, we can try to write the characteristic polynomial, right? What would that look like? 2 minus lambda times 2 minus lambda minus 0, right? Because I need to replace the diagonal with, I need to subtract lambda off the diagonal and then take the determinant. So this is my characteristic polynomial. And I just have one solution. So here I only got one eigenvalue. Okay. But what are the eigenvectors? Okay, if I do A minus 2i, I get this crazy looking matrix. It's just all zeros. It's all zeros. Which means what is in the null space of this matrix, right? That's how I find my eigenvectors. The eigenvectors live in the null space of A minus lambda I. For the values of lambda that work, that are solutions to, determinant of A minus lambda I equals 0. A null space is everything, right? Because everything gets sent to 0. Any linear combination, another way of saying it is any linear combination of columns equals 0 is all of R2. So here my eigenvectors lived along the two axes. Here my eigenvectors live everywhere. Everything is an eigenvector. So here we would say lambda equals 2 has geometric and algebraic multiplicity. Two, right? Algebraic multiplicity 2 because it occurred as a double root of the polynomial. Geometric multiplicity 2 because the space of eigenvectors, the eigenspace, which again is the dimension of this null space. So this is 2. The null space of A minus 2i was 2. You had a two-dimensional space. So again, that's still a nice situation. What about this one? A equals 1, 1, 0, 1. This is a linear transformation called a shear. What does it look like? Well, 1, 0 just gets sent to itself. 0, 1 gets sent to 1, 1. So see, it sort of shears. Oh, I don't want to use the name of the transformation itself, but sort of tilts everything that way to the right. Okay. But you see, I mean, one eigenvector is pretty obvious, right? 1, 0 just gets sent to itself. So that's definitely an eigenvector. What is my characteristic polynomial here? Again, I subtract off lambda from the diagonal, and then I take the determinant. So I get 1 minus lambda times 1 minus lambda minus 1 times 0, but that's just 0. And I set that equal to 0. This just has one solution again. Lambda equals 1. So let's look at A minus 1 times I. That's this matrix. What is the null space of this matrix? The null space of this matrix is just one-dimensional. See, we have rank 1, so it cannot be more than one-dimensional. Here's one vector in the null space. Right, just take one of the first column and none of the second column. Sorry, it's the span of this. Okay, so where do my eigenvectors live? My eigenvectors are just along this line. Okay. So we only got one. This is really interesting though, because this lambda had algebraic multiplicity too. But it has geometric multiplicity. One. Okay. The eigenspace associated to that eigenvalue. Okay, this is the eigenspace, E1. The eigenspace associated to that eigenvalue is just one-dimensional. So lambda equals 1 just gives me a one-dimensional space of eigenvectors. Contrast that with the previous example. Lambda equals 2 actually gave me an entire two-dimensional space of eigenvectors. Everything is an eigenvector for this transformation. You can see that geometrically also, right? This expands space by a factor of 2 in every direction equally. So everything is going to get expanded by 2. Okay, so yeah, this is kind of what can go wrong here. All right, is that everything I want to say? Oh, let me give you a useful fact. This is really useful when doing these calculations. So you can't just look at a matrix and see the eigenvalues right away usually. You have to do that calculation, determinant of A minus lambda equals 0. But here's something useful. The product of the eigenvalues is the determinant of A. Determinant of my original matrix. And the sum of the eigenvalues is something called the trace of A. And the trace of A is very simple. It's just a sum of the diagonal entries of A. This isn't too important, but it's often useful if you want to quickly calculate eigenvalues. So I'll just show an example. So like here, you see the product of the eigenvalues is the determinant. What's the determinant? It's 6 plus 10, which is 4. So the product is 4. Let me write that up here. Product is 4. The trace is 5, 6 plus minus 1, right? And that 5 should be the sum. So I know my eigenvalues will have product 4 and sum 5. So that has to be 1 and 4. So that's what we got down here. And there's nothing profound here. Like this is, you just get this by looking at the characteristic polynomial factorial right here. Because this number is going to be the sum of the roots, and this number here is without the minus sign, and this number here is going to be the product of the roots. But then you just trace back and see where that 5 came from and where the 4 came from. Okay. There's one thing I haven't talked about yet, which is what if we get. So we talked about you might not have any eigenvalues, right? Like the 90-degree rotation. But what about if we get the eigenvalue 0? What about that? Well, if 0 is an eigenvalue, so if 0 is an eigenvalue, what does that mean? It means that A minus, if I take the determinant of A minus 0 times the identity, so again, determinant of A minus 0 times the identity, I get something. I get 0, right? But 0 times the identity, that's just a 0 matrix. So it's saying the determinant of A is 0. I think we can add a line to our unifying theorem. Well, let's go back to this for a second. So if 0 is an eigenvalue, the determinant is 0. Here we have everything phrased in terms of being invertible, determinant not being 0. Right? So if the determinant is non-zero, that's how we should say it maybe. So if the determinant of A is not 0, that's equivalent to 0 not being an eigenvalue. That's the line I'm going to add. Okay. So if all these things are true, or if any of them are true, then we can say that 0, so lambda equals 0, is not an eigenvalue of the matrix A. Okay. Okay, so there's a lot more to say about eigenvectors, but let's leave it at that for now.